What is going on, guys? Hope you're doing awesome. In this video, we will go through how to do image segmentation in PyTorch. And this means that we will, set up everything from scratch. So we're going to build a model, and that the model is going to be very similar to UNet. And then we're going to set up our data loading pipeline, which will include doing data augmentation for segmentation tasks. And for that, we will be using the Albumentations library. So if you're new to UNet, if you don't know what that is, or the Albumentations library, then I have separate videos for both of those, which you could check out. And then lastly, we will train this model on the Carvana dataset, which is a Kaggle competition from a few years back. All right, let's roll that intro and then let's get started with the model. All right, so let's just create a model.python file. And maybe before I start, let me just talk a little bit about the differences that are going to be in our implementation versus the paper. So here's an image that I went through on the paper review video. But so the major difference is going to be that we're going to use padded convolutions because it's going to simplify a lot. Maybe not for the model, the actual model implementation. It's pretty trivial to just change the padding to 0 and then you'll get a valid convolution. But the major difference is that when we're doing the data loading part, that's going to be much more difficult if we use this valid convolutions. So you would need to implement this mirroring padding, which might not be too challenging. But when you have larger images, you're gonna have to do sort of a multi-crop of your image and then sort of stitch that up in some way afterwards. Just makes things a lot more complicated. And when you think about the fact that the winners, for example, for the Carvana Kaggle competition, they used same convolutions in their implementation. And I think the prize was $30,000 or something like that. And you can only imagine that if their accuracy would have improved using valid convolutions, then that's exactly what they would have done. So, we're not losing too much performance here. All right, that's enough rambling about the architecture. Let's just get started. So what we're going to do is we're just going to start with import torch torch.nn as nn. And we're also going to use import torch vision.transforms.functional as tf. All right, so looking at the architecture right here, you can see that the first thing that they do is that what they do in sort of all of these steps is that they use two convolutions in between. So they have some input, they run it through two 3x3 comms, and then they do similar right here, similar right here, similar right here, and similar on the opposite side. So one idea is that we can create a class, which we'll call double convolution. We'll inherit from nn module. We'll create our init function. That's going to take in some in channels and some out channels. And we'll just call super first of all, double conv self.init. All right. So all we'll do here is just self.conv equals a sequential model, which will use a conv2d with some in channels, some out channels. We'll set the kernel size to 3, the stride to 1, and we'll set the padding to 1, which will make it a same convolution. So, I'm assuming you know what same convolution is, but that means just that the input height and width is going to be the same after the convolution. I'm going to set bias equals false here also, and the reason for that is because I'm going to use batch norm. And so in the original paper, I think the paper was from 2015, and I think batch norm, the batch norm paper came in 2016. So of course they didn't use batch norm, but I figured that there's, it would only be beneficial. So let's use it. And so we're using bias equals false just because we're using a batch norm. So it's just an unnecessary parameter to have a bias because it's going to be canceled by the batch norm. All right, that's just a detail. But yeah, then we'll use a relu. We'll set in place to true, and we'll just copy paste this right here and do out channels to out channels for the second conv, and that is it. So we'll just do forward. Forward is going to take some input x, and we'll just return self.conv of x. All right, so what did we do? Well, we created this step that are going to be sort of intermediate between these. And so what we want to do here is just a self pool, right? We just want the max pool, stride 2, kernel size 2, and then again use these double convs in between. So we'll just create our class unit. We'll inherit from nn module. Again, create our init function. And let's see, so we're going to have self, we're going to specify some in channels. In our case, our in channels is going to be 3. So let's just set default to 3. The out channels is going to be 1. So in the paper, they had out channels to 2. And well, I guess, I mean, this is a parameter you can choose, but we're going to do sort of a binary image segmentation. Of course, you're going to be able to extend this to several, but the difference here is that when we're doing binary, we can just output a single channel. So let's just set output channels to 1 as default. Then we're going to specify some features, and these features right here is going to be sort of the features right here. So 64, 128, 256, 512, and then they're going to be exactly the same on the upward. So we'll just set 64, 128, 256, and 512. Like that. All right, so then what we'll do next is call super. Can't forget that part. So super init. All right, and then what we're going to create is we'll create 2 lists. So we'll call them self.downs, and we'll create a list. But you can't just use a list like this because we're going to be storing the sort of the convolutional layers and all that stuff. And then what we got to do is use a module list. And I guess why this is important is because we want to be able to do what is it called, like model.eval and stuff like that. And then we need so for the batch norm layers and so on. And that's why it's important to have this module list. So we'll just have one for ups, and we'll have one for downs, and then we'll have a pooling layer. So let's just do max pooling 2D. The kernel size will be 2, stride will be 2. And so let's just do the down part of unit first. So for the down part, what we'll do is we'll go through the features. So for feature in features, and we'll do first self.downs.append. So we'll add a layer to this module list. It's going to be a double conv, and it's going to be in channels, right? Because this double conv that we just created takes some in channels and some out channels. So we'll just send in channels as initial, and then feature, right? Because it's going to be, if we look at the architecture, it's just going to map some input, right? In this case, 1 that they had to 64. And that's exactly what we have, right? So in the beginning we have 3 here, but it's going to map 3 to 64. For the next feature, we need to make sure that we set in channels to feature, right? So this is going to go through the loop, depending on all that we have in those features, and it's gonna do all those conv layers. All right, and we're going to use this pooling layer in between in our forward method, but you'll see that pretty soon. So what's next? So we gotta create the up part, and what we'll do here is we'll just go through the, so if we look right here, what we just did is create all of these steps right here, and this at the bottom here will create sort of outside of the for loop. So we'll we'll do that pretty soon. So for the upsampling part, we're going to be using transpose convolutions. What you could also do here is just use a sort of a bilinear and then a conv layer afterwards. And that's sort of what they've started to, or they've done it for a long time. But if you look at GANs, for example, in ProGAN, they realized that transpose convolutions create these artifacts, and they started to use that. So I would imagine that would be a better option and a cheaper option probably. But we're not going to do that. We're going to use similar approach to the paper. But so what we'll do is we'll go through the features. And what's important here is that obviously we're going to go from the bottom and up. So we'll do for feature in reversed of features. In our com transpose 2D, we'll set the in channels to be feature times 2. And the reason for this is because we're going to be adding the skip connection. So it's going to be 512 times 2. And that's going to be the case for all of the transpose. We're going to concatenate along the channel dimension, sort of this gray skip connection right here for all of those sort of up layers. And then the output is just going to be feature. So as you can see, it's right here, it's 512. And then here it's 256, and then it's 128. So we'll just do it to feature. The kernel size is going to be 2. Stride is going to be 2. So this will sort of double the height and the width of the image. All right. What we'll do next is we'll just append also a double conv. So we'll do feature times 2 to feature. And so why we're doing that is because we're going to do up, and then we're going to do 2 convs, up, 2 convs, up, 2 convs. So that's why we're doing appending this right here. And let's see, so what's missing right now is sort of this at the bottom right here, which I'll call a bottleneck layer. So we'll just do self.bottleneck is equal to double conv of features minus 1. And so why we're doing features minus 1 is because we want this 512, right? That's the last in our features list. And we're going to map that to features features minus 1 times 2, right? So it's going to be 1024. And then for the last thing we're going to do right here at the top, we're going to this sort of the absolute last thing we're going to do is a final conv, which is going to be a 1x1 conv, and it doesn't change the height and the width of the image. And really what it does is just change the number of channels. So we'll do a final conv. That's just going to be a conv 2D layer of features of 0 to out channels. And the kernel size of that is going to be 1. All right, hopefully I didn't go through this too fast. So that's just the init part. Now we've created all of the modules that we're going to need for the forward step. And so let's do it. Define forward self comma x. And what I'm going to do is I'm going to create a list. I'll just call that skip connections. And you guessed it, we're going to store all of the skip connections in that one. So let's see, what we're going to do is we're going to do for down in self.downs. So, that's the downward part, right? That's what we do first. And for the downward part, we just do x equals down of x. Then we add the skip connection, right, before the downsampling. So we do these 2 convs, add the skip connection to that, which we're going to use later on. And we do that for every part. So skip connections dot append x. And I guess the ordering is important to know here. The first is going to be the one with the highest resolution, and then the last will be with the smallest resolution. And what we'll do next is self pool of x. And that's it for the downward part. Then we'll go through the bottleneck layer, right? So what we've done in this for loop is we've done all of these steps until we're right here. So we've done the pooling, and we just want to do this double conv right here. and this double conv will be a the self.bottleneck. All right, and all right. So one thing we're gonna do just to make this skip connections a little bit easier is because obviously we want to sort of go backwards in that order when we are doing the concatenation. As I said, the first element is going to be the one with the highest resolution. So I'll just reverse that list. So skip connections, we'll go and do skip connections and then just reverse that list. And then what we'll do is we'll go through the self.ups. So the self.ups that we created, we added a conv transpose 2D, and we also added the double conv. So what I'll do here is I'll do for index in range of 0, length of self.ups, and then we'll do a step of 2. All right. And the reason for that is because I want to do the up and then double conv. So up and double conv, and that's going to be sort of a single step. And that's why we're using a step of 2 here. Again, there are probably better ways of doing this. Let me know if you think of a better way to do it. But so what we'll do is we'll do self.ups of that particular index. So 0 in the beginning, right? We'll do of x of that. And what we're doing here is we're doing the conv transpose 2D, right? What we'll do then is we'll add the skip connection. So we'll do skip connection equals skip connections of index integer division by 2. And why we're doing that is just because we're doing this step by 2 right there. So obviously we want to still take the skip connections in a linear sort of a step of 1 ordering. So that might be a little confusing, but nothing too difficult there. Then we'll concatenate them. So we'll do concatenate skip. Sort of concatenate the skip connection. We'll do torch.concatenate skip connection and the x, and we'll add them along the channel dimension, right? So we have batch, channel, height, width. So we'll add them along dimension 1. Lastly, we'll just do self-ups of index plus 1 of concatenate skip. Right, that's it. So what we're doing here is we're doing the upsampling. All right, so following this, we're doing the upsampling, we're concatenating. So we're getting the skip connection, and then we're concatenating. Then we're just running it through this double conv. And then the last thing we're going to do is just return self.final conv of x, right? So I think sort of we're done, but I guess one improvement we could make here is let's say you're not inputting something that is perfectly divisible by 2 at every step, right? That's what is going to happen for this self.pooling layer. So for just to give a concrete example, let's say we input 161 by 161. What's going to happen here is that the max pool is going to take this into an 80 by 80. So it's going to floor the division by 2. But so we have 80 by 80, and obviously when we then upsample, that's going to create an output. So the output will be 160 by 160, meaning we won't be able to actually sort of concatenate the two, right? Because they need to have the same height and width. And that's a problem. So you could solve that by always choosing an input that is perfectly divisible, or I guess divisible by 16, because it's going to be 4 steps, right? So 1, 2, 3, 4. All of those are going to be divided by 2. So that's one solution. But of course, we want to make our implementation general in that way. So what we can do is when we're concatenating them, we can just check right here if they don't match. So if x.shape is not equal to skip connection.shape, then you can solve this by different methods. In the paper, which is a little bit different, but they used cropping right here. What you could also do is you could add padding. And what I did is I'll just do a resizing. So I'll use this TF, the torch vision functional, and we'll do tf.resize of x, and then we'll just set the size. So if you think about it, the x, which is coming from the sort of the upward part here, it's always going to be smaller than what was, you know, downsampled, just because of that reason that max pool always floors the shapes. So I guess it's just important to resize the x, and I don't think this is going to impact the accuracy too much, I hope, because, you know, it's just going to be, you know, sort of a 1 pixel difference, and so I don't think it matters too much. I haven't tried this extensively though, but so skip connection dot shape. So what we'll do here is we'll just take out the height and the width. So we're skipping the batch size and the number of channels. But that's all we have to need for the resizing. All right, so that was, you know, unit in, yeah, I guess 67 lines of code. Not too bad. And hopefully it's understandable and readable still. So we'll just create a test right here. The test torch.random. Let's say we have a batch size of 3. Input, let's see, 1 channel. And then we'll do, I don't know, 160, 160, which is perfectly divisible. Then we'll do model unit. In channels we'll set to 1. Out channels we'll set to 1. We'll do predictions is model of x. And what we want to do or make sure is that the input is the exact same shape as the output. So we'll just do print preds.shape, print x.shape, and maybe also assert preds.shape equals x.shape. And we'll do if name equals main. Then we'll run that test right there. All right, pretty good. Let's see if we can run this now. And we get the exact same shape, meaning no errors were done during this. That's amazing. I always make mistakes. All right, pretty nice. So what we're gonna do next, I think, is we'll look at the data and we'll set up the data loading part, and then we'll actually do our then we'll do the training, set up the training. So let's just create one called Dataset. And what I gotta do first here is actually copy in. So this is the code that I've written beforehand. What I'm gonna do is I'm gonna copy in that data into our folder right here. All right, so what I've done is just put in the data right here. And this, you can download this from Kaggle. All I've done here is I've just taken the training images, which look like this. And let's see if I can pull this up. So that's how they look like. And what they want is the segmentation for the car. And so, you know, the training masks looks like this, which is binary, just black and white. And then what I did is I just took sort of a couple of examples, 48 examples to be specific, to a very small validation set. So that's how the data set looks like. You can download it from Kaggle. There's going to be a link in the description. So what we want to do now is set up the data loading part. All right, so for that, we're going to use OS. We're going to import pill. I guess from pill import image. Then we're going to do from torch utils.data import dataset, import numpy as np. And I just thought of one thing we could do actually on the model. So in the model right here, I chose this 160, which is perfectly divisible. Let's just do 161 and make sure that it still works for the model. Yeah, and there's no error, right? So the assertion was okay. And that means that our resizing also worked. Anyways, moving on. So we're going to create a class. We're going to call it Carvana Dataset. We're going to inherit from Dataset. Let's create the init method. So what we'll take in here is the image directory and a mask directory. And we'll also set transform to none by default. Then we'll just do self.image directory is image directory. and we'll just copy paste that 2 times. We're going to do same thing for the mask directory. All right, so now we have the transform, all that. What we will also do is we'll do self.images is OS list directory of image directory. So that'll list all the files that are in that folder. So for the length of that data set is going to be pretty simple. We'll just return the length of self.images. For our get item like that, we're going to take as input some index, and what we'll do is we'll first get the image path, which is going to be OS path join of the image directory, so where we store the images, and then also the file of that particular image. So that'll be self.images of index, right? Hopefully you're following so far. For the mask path, pretty much the same thing. So OS path join, but now we'll do self.mask directory, and we'll also do self.images of index. But the only difference here between, so I didn't take a look at, show you exactly, but for the train masks, it has the same name, but at the end it just has an underscore mask, and instead of being a, I think, JPEG or PNG, it is actually a .gif, so we gotta adapt to that. We'll just do self.images.replace, and all we'll do here is .jpeg, and we'll change that to underscore mask.gif. All right, so now that we have the mask path and the image path, we'll just load those two. So image equals numpy array of image.open of image path, and yeah, we'll also do .convert to RGB here. I think it's by default RGB, so we might not have to do this, but just make sure. And also why we're doing numpy array here is because we're going to be using the augmentations library, which if you're using pill needs to be converted to a numpy array. So we'll just do mask equals numpy array of image.open mask path, and then we're going to do .convert L. And the reason why we're doing L here is because the mask path is going to be grayscale, so that's how you do that for pill. And one more thing also is we'll specify the D type to be npfloat32, right? So this is going to be loaded as images between, so the, I guess it's going, so most are going to be 0, and then some elements are going to be 255 for the white parts. So what we'll do is we'll just create some sort of a pre-process for the mask, and we'll look for the mask where it's equal to 255, and then we'll change that to 1. So the reason for that is because we're going to use a sigmoid on our as our last activation, and so indicating the probability that it's a sort of a white pixel, and then to make sure that it's actually the correct for the labels, we'll just convert those to 1. All right, we'll just do if self.transform is not none, then we'll perform the data augmentation. This is using the augmentations library. So we'll just do augmentations is self-transform of image equals image, and then mask equals mask. And so this, you should be pretty familiar with this if you watched that video. Otherwise, you know, we're just sending in the image and the mask, and then to obtain the image, we'll get the augmented image from the dictionary with the key image. And similarly with the mask, all we'll do here is just change that to mask. Pretty simple, to be honest. And then return image and mask. All right, pretty cool. That's for the data set. And so what we've done so far is create the model and the data set. I guess what we'll move on to now is create the training part. All right, so let's just create a new file called train. And I'm gonna copy paste in, let's see, I'm gonna copy paste in the imports here. So we're gonna use torch argumentations as A. We're gonna need to tensor v2, TQDM for the loading, for the progress bar, and then we're gonna import our model as well. And yeah, we're also gonna create a utils file where we're gonna import, I guess, load checkpoint, save checkpoint. Let me copy paste in that as well. And we're gonna create those, I guess, later on. So we're gonna be using load checkpoint, save checkpoint, get loaders, check accuracy, and then save predictions as images. So we'll create those later on. Just I'll comment that for now. And for hyperparameters, I'm gonna copy paste in those as well. So I'm just setting the learn rate 1e-4, device, CUDA if it's available. Otherwise, we'll set it to the CPU. Batch size 32. Might have to decrease that now when I'm recording. Number of epochs, maybe let's set it to 3. Numworkers 2. Image height, I'm just going to set a very small image height. Image height is originally 1280 and the image width is 1918 originally. So we're just going to be using, a very, very small part. But you would just change this if that's, if you were doing the competition and you wanted to obtain better score. And yeah, so if pin memory is true, we're going to set load model, set it to false originally. And then just specifying the path where we have the data set. That's the train images and then validation images. All right, so I'll just show you the general structure that we're going to be creating. So the general structure will just have a training function where we will send in some loader, some model, some optimizer, loss function, and also scalar. We'll go through that. But so that's the train function. We'll have a main function, and then we'll do check if name equals main. And why this is important right here is on Windows. You need to do this so you don't get any issues when you're running numworkers. All right, so we could perhaps start with the train function. So the train function is going to do 1 epoch of training. And we'll use TQDM here for a progress bar. So we'll just do a loop is TQDM of loader. And if you're not familiar with this, you don't have to do this, but I have a separate video on TQDM for a progress bar as well. So we'll just go through for batch index and then data and targets in enumerate of that loop. And what we'll do is we'll just get it to CUDA, so data.to device equals device. Same for the targets. Also, one thing we need to do for the targets is convert it to float. It should be float, right? Yeah, it should be float. For some reason, it might not. I don't really remember, but I think it's important for the binary cross entropy loss that we're going to be using. Yeah, so I'm just converting it to float. I think I got an error for that or something. All right, we'll just do unsqueeze 1, sort of adding a channel dimension, and then we'll do toDevice equals device. All right, so for the forward, we'll use float 16 training, which I have a separate video on how to do. But so float 16, just sort of reducing our VRAM and speeding up training. So it's not too difficult to do either. We'll just do with torch CUDA amp autocast. We'll get the predictions by doing model of data. The loss, we'll send in loss function and the predictions, comma targets. For the backward, we'll first do 0 grad, 0 all the gradients from previous. We'll do scalar.scale of loss.backward, and then scalar.step of optimizer, and then scalar.update. All right, and then we'll do we can update the TQDM loop showing the loss function so far. So we'll do loop.set postfix loss equals loss.item. All right, so that's for training one epoch. In our main function, I'm going to, let's see, I'll copy in those two just because I've covered it in the albumentations library when I did that video. But so all I'm doing here is we're doing a resize to the height of image height, image width, which we wrote at the top. And then we'll do a rotation, horizontal flip, vertical flip, normalize. Here we're actually just dividing by 255, so we're getting a value between 0 and 1. And then to tensor. And similar for the validation, although we'll just resize and normalize. Right? So that's all we're doing here. Very similar to PyTorch, nothing really difficult here. All right, so next we'll just create our model, which is going to come from unit, which we created. So in channels is going to be 3, out channel is going to be 1, and we'll get that to device. The loss function is going to be a BC with logit loss, and so binary cross entropy. And why we're using with logit is because we're not. So on our output, we're not doing sigmoid. You could remove this with logit loss if you did right here, if you did torch.sigmoid on the model or the output of the model. All right, and then, so what would you do if you were extending this, if you wanted multi-class segmentation? All you would do, you would change the out channels. Let's say you had 3 different colors, 3 different classes. You would change this to 3. You would change the loss function to a cross entropy loss, and that's all, right? So, this is very easily extendable to multiple classes. Let's just do that for now. And then we'll do our optimizer. So our optimizer, we're just going to use Atom with model.parameters, learning rate equals learning rate. All right, so to get our loaders, obviously we could do, Carvana dataset and then data loader of that. I think it looked a little bit ugly. It took a little bit too much space on this main function. So we're just going to do train loader, comma val loader, and we'll run get loaders. And I guess here we're going to send in the train image directory, train mask directory, the validation, and the batch size, the transforms that we're going to perform, and then the val transforms. So we'll go to that, create that utils file and do that. But I guess we could finish this as well. So we're going to create that pretty soon. First, we want to do scalar is torch.cuda.amp.grad scalar. We'll go through for epoch in range of num epochs. I guess also we need to send in here, we're going to send in num workers and also pin memory. All right, so for epoch in range of num epochs, we're going to call our train function, which will just send in the train loader, the model, the optimizer, the loss function, and the scalar, right? Nothing too difficult here. And let's see what we need to do else. So I guess one thing, what we'll do later on is we'll do save model, we'll do check accuracy, and then we'll do print some examples to a folder, and then we'll just see that it actually looks good. But so first, let's create this utils files now. So utils, And I'll just copy paste in the import. So the import Torch Vision, Torch, Carvana dataset, right? And then the data loader. I'll paste in two files right here, which is two functions rather, which is save checkpoint and load checkpoint. Again, I also have separate videos on that if you want to check that out. And I'll also copy paste in the get loaders, and I'll go through it. So the reason for this is I think this is honestly pretty simple. All we're doing here is we're creating the Carvana dataset. We're specifying the transforms and all of that, the image directory, mass directory. For the train loader, we're specifying the training dataset, batch size, num workers, pin memory, and then shuffle. Similar thing for the validation. So the difficult part here was actually creating that Carvana dataset, which we did before. And all we got to do is just create similar for the validation loader, and we won't shuffle that one. And then just return train and loader. I guess we could do the check accuracy. That might be a little bit more difficult. So we'll send in some loader, some model, some device, default CUDA, and we'll check first. So the number of correct is going to be 0. Number of pixels we'll set to 0. So, you know, remember for segmentation, we're outputting a prediction for each individual pixel, the class for each individual pixel. So what we'll do is we'll just, we'll get to that. So, and then we'll also do model.eval. We'll wrap everything with a torch no-grad, and then we'll go through that loader. So for x and y in loader, we'll do x dot to device, y to device. We'll run through the model, so we'll get some predictions, which is torch sigmoid of model of x, right? Then what we'll do is we'll convert all those that are higher than 0.5 to 1. All those less than that will convert to 0. Obviously, you would need to adapt this check accuracy to if you would have more classes, but don't think that would be too difficult perhaps. But just know that this is for binary. So we'll do predictions is predictions greater than 0.5, and then dot float. All right, we'll do number of correct is plus equals the predictions that are equal to y, and then sum. So that will sum all of the pixels. Then the number of pixels that was in that image is going to be plus equals torch dot number of element numal of predictions. And yeah, so then we'll just print you know, an f string got number correct divided by number of pixels with accuracy, and then let's just do num correct divided by num pixels, and we'll multiply that with 100, and then with 2 floating decimals. Yeah, so that's it for the accuracy. One thing I actually want to do here as well, which if you don't follow this, it doesn't matter too much, but one thing that's kind of flawed when doing the accuracy is that if we just output sort of just black pixels, it will have an accuracy of greater than 80%. So they found that there are better metrics for measuring this, you know, similar to object detection using intersection over union and so on. It's a better metric. They also found that there's a better metric for this, which is using a dice score. And this is just one line, so I'm just going to add it. But what it is it's going to be 2 times sort of the pixels where they're both outputting a sort of a white pixel. So we're going to just element-wise multiply them. So where they are the same, they're going to be output 1. We're going to sum those two. So we're summing the number of pixels where they are both the same. or both outputting a white pixel. Then we'll divide that by predictions plus y dot sum. So we're dividing by the number of pixels that they're outputting 1 for both of them. And we'll just add a epsilon of 1e minus 8. Yeah, so yeah, actually I don't know too much about die-score. This is just for binary, so it's pretty simple here. You can probably Google and find out how you do it for multi-classes. And so we'll just use this for now, just knowing that it's a little bit of a better measurement to evaluate how good it is. But if you don't follow this, don't bother too much about that. All right, and then we'll just print die-score. We'll do die-score and then divide that by the length of the loader. All right, and then we'll set model.train again. All right, so that's the check accuracy. For the save predictions as images that I also imported, I'll copy paste that in. And so what we're doing here is we're just going through and then outputting the prediction and the corresponding sort of correct one associated with that one. It doesn't matter too much here. This is just so that we can get a visualization of what it's doing. All right, that was probably too fast, but yeah. What we'll do now is we'll just remove from Utils, we'll just import all of that stuff. And yeah, so now we can, in our, right here, we can save the model and we can do all of those things that we wanted to do. So for saving the model, we'll create a checkpoint. We'll just do state dictionary, model, state dictionary. We'll also store optimizer, state dictionary. Then save checkpoint of checkpoint from the utils file, and then check accuracy. We'll just do check accuracy of validation loader, send in the model, send in the device, and then we'll print some examples to a folder. So let's do save predictions as images. We'll send in the val loader, model. The folder will do saved images. And then the device is just a device. So what we'll do here is we'll just create a folder right there, directory, called saved images. And yeah, that should be it for this one. And there are probably going to be some errors, but you know, that's how it is. So let's try and run this now. Wow, it actually worked on the first try. I mean, I haven't made a single mistake this entire video. That's insane. Yeah, so we're not using the load checkpoint. I guess what we can do in the meanwhile is also, let's see, right here maybe, we'll do if load model, we'll do load checkpoint of torch.load of my checkpoint. That's just what I call the file. My checkpoint.pth.tar and then model. Yeah, I'll just let it run and we'll see how good it is at the end of training. All right, so I also noticed now after one epoch, the accuracy stuff is actually wrong. And I wonder what we did wrong there exactly. I think we missed to do one thing, which is that we got a .unsqueeze 1 right there. And the reason why we have to do that is because the label doesn't have a channel because it's grayscale. So we just have to do .unsqueeze and then the accuracy should work. So now it's just outputting rubbish, but the die score should be okay. So what we'll do is we'll just let this train until it's done, and then we can rerun it and evaluate and see what we get for the accuracy and the die score. All right, so now that it's trained 3 epochs, what we'll do is we'll just copy this check accuracy. We'll put it just after we load the model. And then I guess we'll go to load model and we'll just change that to true and rerun it and see what we get. All right, so we see that we get an accuracy of 99.52, and we've just trained 3 epochs. We get a dice score of 98.7, and you can just train this for longer and it would definitely improve. Then you would change the image height, image width, make it larger, and that's probably what I would do. And then maybe perhaps consider adding more data augmentation. But yeah, so I mean, this is for sure working. Let's see if we can look at some saved images. So here are some predictions. Let's put them side to side. Yeah, all right, so here it is. So at the right, we have the correct target segmentations. On the left, we have the predictions for the corresponding targets. As you can see, it's obviously very close to being correct, which is why it also has that good of a score. I think that what the winners had of that Kaggle competition was 99.7 in dice score. So obviously we're pretty far off. Yeah, and also we're looking at smaller images. What you would do is you would want it for these original images, and then you would just do a resizing. And yeah, so that would, and I guess the resizing has to be done with a nearest interpolation. But yeah, so what we did was a lot in this video. It's probably going to be quite long, but if you consider all that we did, I think it was pretty compact. We built the entire structure from scratch, the model, the data set loading part, all of that stuff, and we trained it as well. All right, that's it. Thank you so much for watching the video. Like the video if you thought it was good, and yeah, see you in the next